Alright, well, I am back. Let me know if that helped at all. I hope it did. If not, then it was kind of a waste to start over, but it was worth trying because I know the delay was pretty bad. Alright, now, back to what we were doing is going through these problems. And so the next one we're going to have is, suppose that n is in z. I want to show that 5n squared plus 3n plus 7 is odd. All right. And so what we have is we have n is an integer, and we want to show that, so we get to assume the if part. So assume n is an integer. I want to show that then five n squared plus 3n plus 7 is odd. Alright, so I'll let you guys look at this a second and think, well, if n is an integer, how are we going to prove that that's odd? What are we really assuming there? What do we get? Is that's actually a fairly difficult problem because we don't really get to assume that much. So if we don't get to assume that much, how in the world are we going to prove that? Well, we have to come up with some things that are going to work here. And so the way I'm going to do that is I'm actually going to work backwards. And so to work backwards, what I'm going to say is, well, if I want to show that this is odd, then what I have to show is that this is equal to 2 times an integer plus 1, or it's congruent to 1 mod 2. That is, it's not even. And so there was a whole list of things that we did last time. And to stick with the way I was doing things, I'm going to actually say this is congruent to 1 mod 2. So if I want to show that this is congruent to 1 mod 2, based on the fact that this is an integer, I have to work with, well, what does it mean for n to be an integer? Now, because n is an integer and I'm working mod 2, I know that my only possibilities are that either n is congruent to 0 mod 2, or n is congruent to 1 mod 2. So the idea here was I started at the end and I said, okay, this is what I need to prove. If I think about integers, there's only two options. It's either 0 or it's 1. So I don't get to assume a lot, but I do know that it's either 0 or 1 because those are my only options mod 2. But because I have an or here, what I'm going to have to do is I'm going to have to do this proof in cases. So case 1 would be n is congruent to 0 mod 2. Case 2 would be 1 is congruent to 0 mod 2. So if I can show in both cases this is true, well, those are the only two possible cases, therefore it will always be the case that this is true. So case 1 we'll say is n is congruent to 0 mod 2. We have to show that this is congruent to 1 mod 2. So what we're going to have is 5n squared plus 3n plus 7, and we somehow have to get out 1. All right, so I'm going to do a very similar thing to what I did in the first problem. Was I'm going to erase this so I have some room. But since I'm working mod 2, what I could do is anywhere I have a number, I can replace what it's congruent to mod 2. So 5 is congruent to 1 mod 2 because 5 is odd, so it's congruent to 1. N is congruent to 0 because we assumed as much, so instead of n, I can write 0. And then I get 3 is congruent to 1 mod 2, and n is congruent to 0. and 7 is odd, so it's congruent to 1 mod 2. So over the whole thing, I replaced what each of the numbers were with what they are congruent to mod 2. So as such, I get something that's a little bit easier to deal with. And I can just take 1 times 0 is 0, plus 1 times 0 is 0, plus 1 mod 2 is just 1 mod 2. Hence, if n is congruent to 0 mod 2, then 5n squared plus 3n plus 7 is congruent to this, is congruent to this, is congruent to 1 mod 2. Therefore, this is odd in this case. The other case I have to try is 1 mod 2. So all that's going to be different here is I'm going to let n be congruent to 1. So instead of plugging in 0, I'm going to plug in 1. Now if I do that arithmetic, I get 1 times 1 squared is just 1, plus 1, plus 1. So I get 1 plus 1 plus 1 mod 2, or 3 mod 2. But 3 mod 2 is congruent to 1 mod 2. So again, in this case, I get that I'm congruent to 1 mod 2, so I must be odd. Therefore, in either case, this is odd. So for any integer n, 5n squared plus 3n plus 7 is indeed always odd. Does that problem make sense to you guys? Do you have any questions on there? All right, I'm not seeing any. So I'll go ahead and move on to the next one here. And what I have is, I want to show that if x is a real number. Oops, did I go too far? Nope, that's the next one. So if x is a real number, I want to show that x to the 5th minus 4x to the 4th plus 3x cubed minus x squared plus 3x minus 4 is greater than or equal to 0. Then it must be the case that x is greater than or equal to 0. All right, as I look at this, I do want to note that I went to the new chapter because if I try to do this directly, what I get to assume is that that big thing, x to the 5th minus whatever, is greater than or equal to 0, and I would have to show that this means that x is greater than 0. Now, how in the world would I do that I honestly have no idea. You'd have to do some type of solution of an inequality with a 5th degree polynomial, and doing such a thing would just be a mess. So that's kind of the point of this chapter, was that we don't always have to do a direct proof. What we can do is a proof by contrapositive. And if we do a proof by contrapositive, what that means is that we're going to assume the negation of the then part and prove the negation of the if part. Because remember, if P then Q is equivalent to if not Q then not P. So we get to assume that x is not greater than or equal to 0, and we have to show that that big equation or inequality thing there is less than 0. So if we assume the negation of the then, we get to prove the negation of the if, and that will give us how to work through this one. So let's actually look at how that works out. I think I made a mistake somewhere in there. Yep, alright, this was supposed to be a 3. So the goal is to show that this thing is less than 0. All right. Instead of trying to do this all at once, I'm going to do this piece by piece. I'm going to start off with assume x is less than 0. What do I know about x to the 5th? Well, what I get is x to the 5th is a negative number. Let's say negative y to the 5th. But if I raise a negative to the 5th, this would be like negative 1 to the 5th, y to the 5th for some positive y. So this is going to end up being positive. So if I just look at negative 1 to the 5th, well, that's just negative 1. So what do I end up with is that if x is negative, then x to the 5th is a negative number. So what does that mean is, well, if x to the 5th is negative, it means x to the 5th is less than 0. Is that okay right so far? A negative number to the 5th is negative, so therefore I get that's true. If I move on to the next one, I get negative 4 times x to the 4th is going to be, well, a negative number to the 4th is positive, but multiplied by a negative number is negative, so this is going to be less than 0. This is supposed to be a cubed here. Sorry, that was a copy error. So I look at 3x cubed. Again, a negative number cubed is negative times a positive is still negative. Negative x squared is a positive because a negative number squared is positive times a negative is again negative. 3 times x is, this is negative times a positive is negative. And negative 4 is just negative. So each one of these terms is less than 0. So this doesn't necessarily need to be written in the proof, but I'm just trying to point out that what I'm noticing here is as I'm trying to go through this, I see this big long thing. Instead of trying to do everything at once, I want to focus on one piece. And if I focus on each of these pieces, I notice that each of these pieces is negative. So what I'm going to get is a negative plus 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 a negative. So if I add a bunch of negatives, I'm going to think, well, that should be negative. And indeed, if we recall something like, let's suppose A is less than B, we can say A plus C is less than B plus C. So if I substitute in the bigger one on the right, I'm going to have the bigger answer on the right. Using these ideas all put together, what I get is just, well, x to the 5th minus 4x to the 4th plus 3x cubed minus x squared plus 3x minus 4 is going to be less than, well, I know that this is negative, so this is less than 0. So if this is less than 0, I can substitute in 0. Plus, if I look at this term, that's less than 0, so I can substitute in 0, and this side's going to be bigger than this side. Again, I can substitute in 0 here, and here, and here, and here, and what I end up with is, well, 0 plus 0 plus 0 plus 0 plus 0 plus 0 is just 0. So what does that mean is that this term is less than this term, which is just 0. Therefore, this whole thing is just less than 0. And so, actually, by doing a contrapositive, all we notice is each of these terms are negative, so the whole thing is negative, and our proof actually follows through very quickly. The big point here is that if we try to do this directly, assuming this is non-negative, showing this is non-negative becomes a much more complicated task. So being able to use a contrapositive and then just noting that these things are all negative is what's going to give us our proof here. Questions on that at all? All right. So then the next one we're going to have is we're going to suppose that a is an integer. I want to show if 4 does not divide a squared, then a is odd. again, the does not divide is tougher to work with than the does divide. We could do this one directly. We could think, okay, if 4 does not divide a squared, then the remainder has to be 1, 2, or 3, because those are the only options. And we could go through case by case and actually show this. But if we actually work with the contrapositive, this becomes a much easier proof. And so we'll actually go ahead and go do that. And what I want to do is the then part is A is odd. Therefore, I'm going to assume the negation of A is odd. So I'm going to assume A is even. Then I'm going to show the negation of the if part, which is 4 does not divide A squared. So the negation would be 4 does divide A squared. All right, so I have to rewrite these things. Now, I do want to point out that we have been using things like A is congruent to 0 mod 2 means that it's even. And this is saying A squared is congruent to 0 mod 4. So if I'm showing it's divisible by 4, that's the same thing as saying it's congruent to 0 mod 4. And so what I would have here is if I wanted to use modular arithmetic here, I'd have to start off with A is congruent to 0 mod 2. And I'd have to show A squared is congruent to 0 mod 4. Now, if I write that down, notice that we haven't done any problems where we change the n. Going from mod 2 to mod 4 isn't actually an easy thing to do in general. So trying to do this using modular arithmetic isn't going to work out because the number at the end of the mod changes from top to bottom. So if you see that, what I would suggest is going back and trying something other than modular arithmetic. So that means I'm going to go back to my definition of even, where even means that 2 divides the number, which means that A is 2 times some number, or integer, k1. And if 4 divides A squared, that means that A squared is 4 times some integer, k2. Hence, what do I do? All right, so I have to figure out how to get from here to here. So now this works back to, okay, well, I have something. I want to show this is equal to something. So I'm going to start on the left, and hopefully I can get out the right. So how would I do that is, well, notice that A is equal to 2k plus 1. So if I want to write A squared, well, A is the same thing as 2k1. So instead of A, I can write 2k1 because they are the same thing. So A squared is 2k1 squared. How is that going to be helpful? I'm not sure, but let's actually square this. So squaring, I would get 2 squared is 4k1 squared. And that's where this is helpful, is because now I get, well, k1 is an integer, so an integer squared is an integer. So I've now written A squared as 4 times an integer. So if I let k1 squared be equal to k2, that just means I'm rewriting this. I'm going to call this k2. Then I have that A squared is 4 times k2 for some integer. Therefore, 4 divides A squared. Now the point here was that we actually tried something and we got it wrong. And there's nothing wrong with that. Or what we tried was wrong because it's not going to work out. It's not going to give us a nice answer. So we tried something else. And that's indicative of how these problems go. You're not always going to get it right the first time through. You try different things until you do get it right. Here we got something that worked. So we have a proof. So now we're happy. Yes, this is true. So we can move on to our next problem. All right. All right, very good. I'm just checking to see if there's any questions. I'm giving a second to catch up. I think there's still a pretty big delay. I apologize for that. I'm not sure what else to do about it. Hopefully I can figure something out for next time. But what we have now is, I'll just go ahead and finish or continue with this one. And The last one was if a is an integer, then I want to show that, sorry, if a is an integer and a is congruent to 1 mod 5, I want to show that a squared is congruent to 1 mod 5. All right, very good. So how would I do this one? Actually, this one isn't too bad because we're just using modular arithmetic again. And again, if you're not used to working with modular arithmetic, this gets more complicated, but what we get to assume is that a is congruent to 1 mod 5, and I want to show a squared is congruent to 1 mod 5. Now, I think this is in the section about contrapositive, but in this case, I really would do a direct proof. So I would actually suggest that you do a direct proof because this is going to be easier that way. And the idea is that I want to show that, okay, if a is congruent to 1 mod 5, then a squared must be congruent to 1 mod 5. And so I'm going to assume that this is true, and I have to show this is true. Now, the nice thing about this one is I don't actually need to rewrite anything. I just have, okay, it's congruent to 1 mod 5, so I can do a substitution. So a squared is going to be congruent to, well, a is just 1, so I substitute it in. So instead of a, I get 1, so a squared is 1 squared mod 5. But 1 squared is just 1. And then lo and behold, I'm done. That's it. It's a really easy one. But it's not so easy if you're not used to working with modular arithmetic and substituting in. So that's really kind of why I gave you this one, is just to work with that, to realize that, yes, there is a utility in getting used to doing this. So get comfortable with it because it will help you along the way as we're writing out different proofs. So that was it. A is congruent to 1, so a squared is 1 squared. 1 squared is 1, so a squared is congruent to 1 mod 5, and we are done. All right. That was all the homework problems. So hopefully you guys are ready to turn in your... All right, so I had a question there about where the 1 was coming from. So I'm going to go back to my chalkboard now. And where are the 1s coming from is this one was coming from a substitution. Whereas this one was coming from just noticing that I'm calculating 1 squared, and 1 squared is equal to 1. So therefore, even in mod 5, 1 squared is still equal to 1 squared, which is 1 mod 5. So I actually calculated that and got my new answer out here. So that's where this one is coming from, is actually calculating 1 squared. This one is coming from substituting in what we assumed in our theorem. All right. That was, as I was saying, that was all of the homework. So I'm actually going to stop there. I apologize for the delay. I'll try to figure out what was happening there and make it quicker for Tuesday, or Thursday rather. On Thursday, we'll start going over some new stuff. But please remember to get your homework in. It's due at midnight tonight. If you need help, we went through all of them here, so you can look through them and just make sure to write them up and submit it so that you have it in on time. All right, thank you guys for joining me, and I will see you again on Thursday.